Welcome to Training Program 10.4a on the IBM Selectric Typewriter. This portion of the Selectric training program covers the printing mechanism, and it also includes the topics of alignment and character selection. In this program, you will learn how to adjust the printing mechanism, how to remove and reinstall tilt and rotate tapes, and how to adjust the tilt and rotate systems. To accomplish this, you will often need to rely on your skills in mechanical reasoning. With this in mind, we will first review some fundamental concepts needed for this program, right along with the explanations of the theory of operation of the printing mechanism. This will make you more aware of the relevance of these fundamentals, and it also makes sure you know exactly what we mean when we use a given term, expression, or concept. Let us start with an overview of the operation of the printing mechanism. All of the printing which the IBM Selectric Typewriter carries out is performed by this one and the same printing mechanism. In this right side view, during continuous printing, the print shaft rotates clockwise at approximately 15 revolutions per second. On the print shaft, we find the print sleeve and a print cam, which provide the power, or the motion, to the print cam follower. The print cam follower rotates counterclockwise and causes the rocker to turn clockwise. The rocker carries, or supports, the element and accomplishes the printing. Basically, there are only these four parts: the cam follower, the rocker, and the type element. Unless your machine is quite old, you will find that the print cam has two lobes for only one print cam follower. The print cam follower may be operated by either one of the print cam lobes. The selection of the appropriate lobe is performed by the input section using the velocity control or velocity selection mechanism. As we examine the lobes on the print cam, we find that both are equal in height, which means that the cam follower is not pushed out of the way of the cam any further with one lobe than with the other. If we examine the print cam from the right side, as shown here, we notice that the difference between the two lobes is that the left lobe starts to move the print cam follower much earlier than the right lobe. Since the RPM of the print shaft is always the same when it is turning, this means that both cams move the cam follower through the same distance, but the cam on the right, in the foreground, does it in less time. The angle for the cam in the background is defined by A, center C, and the angle which starts to operate the cam follower much earlier is defined by B, center C. From this, we conclude that the cam follower has to move at a greater velocity when it has to move out of the way of the right cam lobe. The same is true of the rocker. It, too, has to swing toward the platen at a higher speed when the lobe on the right of the cam, in the foreground, causes it to move. As a result, the lobe in the background on the left side of the cam is called the low-velocity lobe, while the lobe on the right is called the high-velocity lobe. If we measure the mass of the rocker and then multiply the result by the velocity obtained from the cam, we arrive at a quantity called momentum. The greater the momentum of the rocker during printing, the stronger the impact of the type element against the plate, or, for that matter, the paper wound around the plate. The purpose of the double-lobed cam is to provide a means to print characters with a large printing surface, such as M or W, with greater momentum than characters with a smaller printing surface, such as periods and commas. Selectric typewriters equipped with this kind of double-lobed print cam are called dual impression machines, or simply DI machines. Selectric typewriters manufactured before this dual impression mechanism was installed are called pre-DI machines or pre-dual impression machines. In order to see the parts of the printing mechanism we have mentioned, it is best to first remove the ribbon mechanism. If you are using a Selectric II, we recommend that you study training program number 10.5 to familiarize yourself with the removal and reinstallation of the Tech 3 ribbon mechanism and the correcting tape mechanism. For fabric ribbon mechanisms, it will suffice to remove the indicated screws. Be sure not to lose the black retaining springs, which are also held in position by the indicated screws. There is one kind of retaining spring for the right side and one kind for the left side. Without forcing anything, rotate the loosened mechanism into the position shown here, right side to the rear as far as it will go, while at the same time lifting the front, in an effort to bring the ribbon feed cam follower, located under the ribbon mechanism bracket or plate, all the way to the front. You should practice the removal and reinstallation of this mechanism until you become proficient at it, so you do not have to struggle with something which is really a minor project. but which can nevertheless become quite a nuisance when you do not know how to handle it. Without the ribbon support plate in the way, it is easy to see the print cam at the green pencil with its two lobes. The print cam follower is indicated by the yellow pencil. It reaches under the print cam and is mounted onto the right side of the carrier. It pivots on a stud located approximately under the point indicated by the yellow pencil. Be sure to trace these parts on your machine. If you move the carrier of your typewriter over the cycle shaft cavity, you can see the bottom of the carrier and then locate the indicated roller on the print cam follower. Be sure to notice that this small roller can move sideways on the shaft of the print cam follower. This feature enables the one cam follower to operate off either one of the lobes of the print cam. In order to print a character, we must set up our printing operation by carrying out 3 types of selection. We must select the tilt angle, the rotate angle, and the printing velocity. When we studied the keyboard, we learned that the majority of the characters use the high-velocity print cam. This view shows the low-velocity vane located in front of the interposers. For every character with a small printing surface, there is one of these low-velocity selector lugs on the low-velocity vane. Forward motion of the corresponding character interposer will rotate the low-velocity vane top toward the front. On the right side of the keyboard, we find that the velocity control vane transmits its rotation through the indicated link to the low-velocity selector latch, which will also rotate top to the front or counterclockwise. The function of this selector latch is to release a negatively powered or spring-powered mechanism, which will position the roller on the print cam follower into the path of the low-velocity print cam. The counterclockwise rotation of the low-velocity selector latch at the green pencil allows the spring indicated by the red pencil to make the low-velocity cam follower, or low-velocity actuator, follow the shape of the low-velocity mechanism restoring cam, indicated by the yellow pencil. Even a superficial examination of this setup will reveal that the machine must be in a character printing process in order for all this to happen. The low-velocity mechanism restoring cam is mounted on the filter shaft, so it rotates whenever the cycle clutch or print clutch operates. When the machine is at rest, the cam follower is held rotated counterclockwise by the restoring cam. During printing, the cam follower cannot follow the contour of the cam unless the low-velocity selector latch is first rotated out of the way. Most of the time, the low-velocity selector latch prevents the low-velocity actuator from rotating. Locate, at the point indicated by the green pencil, the portion of the low-velocity actuator, which is locked by the low-velocity selector latch. When the low-velocity selector latch is not rotated out of the way of the cam follower or actuator, the amount of motion allowed to the cam follower is very small, as shown by the small clearance indicated by the green pencil. In this photograph, we have half-cycled a low-velocity character and tilted the machine onto its back. To obtain the same condition on your machine, press a comma or a period, and then half-cycle your machine, which means turning the operational cycle shaft by 90 degrees, top to the front. When the typewriter prints a low-velocity character, the rotation of the cam follower pulls the velocity control cable indicated by the red pencil. If we consider that the cable is held by a wire-wound envelope, and that this envelope is firmly held at the point indicated by the green pencil, we realize that the other end of this cable is simply going to be pulled into the envelope, and that this pulling action is performed strictly by the heavy spring which rotates the cam follower. If we now take another look at the position of the roller on the print cam follower, we find that it has indeed been shifted toward the left, hopefully far enough from the front lobe of the print cam. But what if we wanted to know exactly where our cam follower rides on the print cam during a routine print operation? There's a very practical and easy way of finding out exactly where on the print cam lobes the print cam follower rides. By applying grease on the cam lobes and then cycling the machine through a few high-velocity characters and also a few low-velocity characters, it becomes an extremely simple matter to look at the tracks on the print cam lobes and determine exactly where the print cam follower rides. Check your machine and see whether it meets these same conditions. When we want to adjust the position of the cam follower, we need to concern ourselves with only 2 adjustments. Whenever, at the point indicated by the yellow pencil, we cause the wire wound envelope of the velocity control cable to move toward the rear of the adjustment point. We provide a longer path, or tube, for the velocity control cable inside the wire wound envelope. We must adjust the amount of wire wound envelope, which exists between the point indicated by the yellow pencil and the point underneath the carrier, so that there is no slack in the velocity control cable when the machine is at rest. Try changing the adjustment on your machine, and notice that if you feed too much envelope to the right of the adjustment point indicated by the yellow pencil, the position of the roller on the print cam follower is shifted toward the left. The second adjustment, indicated by the green pencil, must be set so that the clearance between the cam follower and the low velocity selector latch is 0.25 millimeters, a quarter of 1 millimeter. Keep in mind that any excess clearance in this adjustment will always be taken up by the cam follower when the machine types a high velocity character. And when this cam follower moves, the roller on the print cam follower also moves. Excessive clearance can cause the print cam follower to track too close to the low velocity lobe, or even on the low velocity lobe, at a time when it should be tracking comfortably on the high velocity lobe of the print cam. Here is the last adjustment of our velocity control mechanism. The screw, colored red, determines the rest position of the cam follower. It is necessary to allow for a clearance between the cam follower and the cam during the time in which the roller is shifted sideways. The indicated set screw enables us to adjust that clearance so that it measures a quarter of 1 millimeter. Again, the way we recognize whether this adjustment is set correctly is that the roller must begin its shift on the lowest portions of the lobes and not before or after these points. Be sure not to exceed this clearance, since otherwise you could bring about a deficiency in momentum buildup for the rocker. Dual impression machines come equipped with one more feature which has an effect on the momentum with which the rocker is swung against the paper. It is called the impression control lever, and it is indicated here by the blue pencil. Notice that this lever has 5 possible positions, which must be selected and preset manually. When the impression control lever is set in the number 1 position, the stud L is closest to the pivot point P of the print cam follower, and the amount of motion coming from F transmitted to L is at its smallest. This means that the distance which L has to travel because of the oscillation of the cam follower is relatively small. However small it is, the distance point L travels must be covered in the amount of time determined by one of the lobes of the print cam. When the distance traveled per unit of time is small, the velocity is small. However, when the impression control lever is set into position 5, the situation is quite different. The distance of travel for L, the load, is now substantially larger. The stud at the bottom of the impression control lever would then be approximately in the position indicated by the pencil. The travel time for this new condition is still determined by one of the lobes of the print cam, which remains the same. We conclude that a larger distance traveled in the same amount of time gives us a higher velocity for the rocker. Or L. This mechanism allows us to build up sufficient momentum to print through various sheets of carbon paper and onion skin paper. There are a number of other details which could still be brought out at this point, but we shall omit them for the sake of simplicity. When multiple copies are to be obtained through the use of carbon paper, the total thickness of the various sheets of paper may require a Platen position adjustment to compensate for the added width, since otherwise certain characters could easily cut the paper. The inclusion of the ABC lever, or multiple copy control lever, solves that problem. By changing the position of the ABC lever, we rotate the eccentric indicated by the red pencil, and, as a result, move the whole Platen support frame forward or rearward. Take whatever time you need to examine this mechanism on your machine, and note that, with the exception of the ABC lever, you will find all of these Platen support parts on both sides of the machine. In addition to being able to adjust the position of the Platen front to rear, we must also be able to adjust it vertically. The Platen height is controlled by the position of the brackets indicated by the yellow pencil. For example, whenever the ABC lever, or multiple copy control lever, is in position A, if a character prints too heavily on the top and too weakly on the bottom, the Platen should be lowered so as to place more rubber, Platen rubber. that is, behind the portion of the character which was printed too lightly. It is important to mention that printing deficiencies can best be checked if the ribbon being used is an old fabric ribbon. Furthermore, we must always be aware that the adjustment of platen height cannot be finalized without previously adjusting the alignment and character selection mechanisms. The routine is to approximate the position of the platen so that the character selection mechanism can be tested. After the alignment and character selection mechanisms have been properly adjusted, then it is possible to finalize the platen position adjustment. If we wish to adjust the basic front to rear position of the platen, we move the multiple copy control lever to the front and then make our adjustment at the eccentric indicated by the green pencil. This eccentric exists on both sides of the machine, and both eccentrics should be positioned at the same angle as much as possible. With this many variables affecting our printing mechanism, it becomes essential to have a reference point from which to begin our adjustments. This is particularly true of the horizontal, front to rear position of the platen. This frame of our adjustment manual tells it all. When the impression control lever, or the ABC lever, is in position A, we can use the depicted platen adjustment gauge. For single pitch machines, the gauge should touch the rear of the print shaft, the platen, and the bottom of the escapement rack simultaneously. For dual pitch machines, the gauge should touch the rear of the print shaft, the platen, and the top of the escapement rack simultaneously. These are starting point adjustments, which can vary according to the specific needs of a customer. When a machine is adjusted to standard specifications, it should meet these requirements. Whenever we change the vertical position of the platen, we need to remember that the platen is held down by the clamp indicated by the yellow pencil. Adjusting only the height of the bracket indicated by the green pencil will not suffice, because the hold-down clamp has to hold the platen against the bracket, since the feed rolls would otherwise continue to hold it up. By the same token, we cannot raise the platen without first getting the hold-down clamp out of the way. Once the horizontal position of the platen and the vertical position, for that matter, has been established, it is possible to make the standard adjustment of the impression control mechanism. When the machine is at rest, and when the impression control lever is in position 4, the distance between the element and the platen should be 6.35 millimeters. As you can see, this distance is easily set using the bent end of the hooverometer. The adjustment for this condition is performed by changing the position of the plate which holds, or detents, the impression control lever. The yellow pencil shows the adjustment screw, which can be reached through the machine power frame and through the side of the carrier. If you have difficulty reaching the opening in the carrier because of the length of your screwdriver, you might want to tab the carrier toward the right until you can reach it with your regular screwdriver. Be sure to check this adjustment on your machine before you continue. It represents the adjustment of the rest position of the type element. Now let us think back for a minute. Can you tell which adjustment must be checked or corrected before we can make this adjustment of the rest position of the type element? If you said the rest position of the print cam follower, you nailed it. It must sit 1/2 of 1 millimeter from the low portion of the print cam. It serves as the fixed point for this adjustment, and the rule is always the same. Check the fixed point first, then adjust the moving one. Your answer should have been the rest position of the print cam follower. The distance between the print cam follower and the low portion of the print cam should be 1/2 of 1 millimeter. Always keep in mind that for every adjustment, there is one fixed point and one moving or adjustable point. In the adjustment of the rest position of the type element, the print cam follower serves as the fixed point, so it is obvious that it must first be in its correct position. Since we did that earlier in this program, we should not have to correct anything now. This rule of checking the fixed point first, of simply following the logical sequence of adjustments, is absolutely necessary for any Selectric serviceman. Consider learning this fact one of the most important things to take from this training program. Throughout his career, a successful Selectric typewriter serviceman has to be able to think along these lines. This is the only wrench which will comfortably reach the eccentric for the impression control lever, which we discuss next. We will need it for the upcoming adjustment. We now turn to the adjustment of the maximum power drive position of the element, or the rocker. When the print cam follower is on the highest point of the print cam, the element should be positioned at a distance of only 0.89 millimeters from the platen. The multiple copy control lever should still be in position. This adjustment can be easily gauged by using the flat end of the IBM spring hook, since its thickness is approximately 0.89 millimeters. The adjustment of the maximum power flight position is performed by rotating the indicated eccentric, which constitutes the pivot point of the impression control lever. Beyond the maximum power drive position, the remainder of the distance between the platen and the type element must be traveled by the element under free flight conditions, in which the momentum acquired during the powered flight, or simply the inertia of the moving rocker, must continue to overcome the tension of the restoring spring as well as eventually produce the impression on the paper. We find both of these adjustments, the rest position of the rocker and the maximum drive position of the rocker, shown in our adjustment manual under the title of Powered Flight and Free Flight. Notice that on the left side, the same frame also contains both of these adjustments for the pre-dual impression machines. While this is a lot of information for just one adjustment frame, you need not let it confuse you. The first adjustment is simply that of the rest position of the rocker, and the second adjustment determines the maximum active position of the rocker. For both, the platen, or the multiple copy control lever, must be in position A. Notice that in the case of the pre-dual impression machine, the print cam is really a cluster of two complementary cams. On pre-dual impression machines, not only the rearward drive of the rocker toward the platen is accomplished positively, but also the return of the rocker into its rest position is accomplished positively. The adjustment sequence, however, is exactly the same, even though the clearance between the platen and the element at the high point of the cam is a whole lot smaller. This means there is much less free flight for the rocker on pre-dual impression machines. Be sure to check the adjustments on your machine. There is no need to change them if you are satisfied that they meet the manufacturer's specifications. The discovery that to every action there is a reaction equal in force but opposite in direction was first stated by Isaac Newton, and for our needs it is just as important today as it always was. Whenever the rocker is thrown against the platen, the body of the carrier is driven in the opposite direction. This means that the carrier bushings, which are hidden under the lubricating pad enclosures, such as the one indicated by the yellow pencil, will take an equal beating unless we equip our machine with a carrier support rail, indicated by the green pencil. This carrier support rail exists on 13-inch and 15-inch machines, but not on 11-inch machines. The wider the machine, the more important the carrier support rail becomes, because the print shaft bends more when printing occurs, while the carrier is somewhere in the middle of the wider machine. The distance between the bottom of the carrier and the carrier support rail should be minimized without creating a drag on the movement of the carrier. The indicated screw is the adjustment screw for the carrier support rail on the left side of the machine. To adjust the carrier support rail, first move your carrier all the way to the left, and then adjust the height of the left side of the rail. Then, simply repeat the procedure on the right side. After you have completed the adjustment, check the freedom of motion of the carrier. Absolutely no bind should have resulted from your adjustment. All of this is quite easy on new machines, but let us briefly look at the older models. On pre-dual impression machines, the carrier support rail also performs the function of the segment ring found on the traditional type bar machines. Whenever we made our ring and cylinder adjustments on the type bar machines, we made them so that the type bar would first hit against the ring on the segment, and then, with a whip action, cause the imprint or impression on the paper. The same feature was designed into the pre-dual impression machines, on which the carrier support bail was called the anvil. The extension underneath the rocker hits the bent portion of the anvil just before printing the character on the paper. In fact, we adjust the position of the anvil on pre-dual impression machines so that when the multiple copy control lever is at 5, the machine must not print a period, simply because the anvil should take up all of the impact resulting from the motion of the rocker. When, however, we put the multiple copy control lever on 4, we should obtain a light print of the period. Of course, the adjustment should be checked on both ends of the typewriter. Adjusting the anvil on one side only is certainly not sufficient. This drawing also shows us the adjustment of the restoring roller on the print cam follower. Notice that when the extension underneath the rocker touches against the lower surface of the horizontal portion of the anvil, the rocker restoring roller should be touching the cam. Since the anvil adjustment no longer exists on dual impression machines, we do not have to worry about it when we adjust the carrier support rail. But on pre-dual impression machines, the rail is mounted according to the position of the plat. With the multiple copy lever on 5, no printing of the period. With the lever on 4, light printing of the period. As mentioned, this anvil also carries out the function of the carrier support rail for the pre-dual impression machines. Once the rail has been set, we simply adjust the buffers that are attached to the carrier so that we reduce the clearance between the anvil and the buffer to a minimum. Again, we must make very sure at the end of our adjustment that no binds in the movement of the carrier have developed. Notice the order of these adjustments. First, the printing and ring adjustments. Then the carrier support adjustments. The platen must be absolutely parallel to the print shaft. We saw earlier that this learning program is divided into 3 sections. The first is printing, the second is alignment, and the third is character selection. With the adjustment of the carrier support rail, we have concluded the printing adjustments of our machine. The reason the carrier support rail has something to do with printing lies in the fact that the action of causing the rocker, which supports the element, to fly against the paper is met by a counteraction, or reaction, on the part of the carrier trying to rotate its front end downward. To prevent the carrier from changing its position due to a bow in the print shaft, we have adjusted the clearance between the carrier support bail and the carrier. With this out of the way, we can turn our attention to alignment of the Selectric typewriter. Alignment is nothing more than a series of adjustments aimed at reducing play, no matter what kind, that may exist in the parts responsible for the movement of the element against the paper. At the time when printing occurs, the element, or for that matter the selected character on that element, must be held very firmly in its position. Any variation of position between one character and the next will produce poor character alignment on the printed sheet of paper. We avoid this by making accurate alignment adjustments. IBM calls these fine alignment adjustments, and justifiably so. These adjustments are quite fine in the sense that they require accuracy. There are 4 kinds or levels of carrier support shoes for the rear portion of the carrier. 3 of them are shown here. On the older machines, at the rear of the carrier, we find a carrier shoe, either square or round with one flat side. The screw which holds the shoe in position is eccentric, so it becomes possible for us to adjust the vertical play at the rear of the carrier. Essentially, we are adjusting the clearance between a lug on the carrier, which extends underneath the escapement rack, and the shoe. This limits the vertical play of the carrier around the rack. Level 2 machines are equipped with a combination carrier shoe and leaf spring. In both cases, after reducing this clearance, we must make sure that we have not created a bind or tight spot in the movement of the carrier. So we must check it all across the escapement rack. This shows a level 3 carrier support bracket. On these later model machines, the carrier shoe no longer exists. Instead, we simply have this bracket fastened to the rear of the carrier. This bracket has 1 lug underneath the escapement rack and 2 lugs above the escapement rack. The spring mounted on the bracket will always keep the rear of the carrier lifted so that the bottom lug of the bracket is always rubbing against the escapement rack, while the spring slides on the top of the rack. Check your machine to verify which kind of carrier support it uses. Whenever a machine comes equipped with a bracket and spring only, there isn't any need for a vertical clearance adjustment at the rear of the carrier. All we need to do in this case is adjust the position of the bracket so that the lugs situated above the rack are also parallel to the rack. Selectric II machines are also equipped with this bracket and spring only. However, at the point indicated by the yellow pencil, the bracket has a slot allowing vertical adjustment of the rear of the carrier. It is important that the height of the carrier be positioned in such a way that the escapement pawl becomes centered with the escapement rack. The height of the engagement of the escapement pawl with the escapement rack is easily visible when you observe the escapement pawl through the right side of the power frame. Again, be sure not to leave any binds in the carrier whenever you have to change this adjustment on any machine. It will cause character crowding or piling. Our second adjustment in the sequence of adjustments needed for the alignment of the characters is that of the end play of the rocker. The 2 points indicated by the yellow and green pencils show the location of the pivot bearings for the rocker. It is necessary that the rocker be allowed to rotate with minimum or absolutely no side play. If you closely examine the space on the right side of the rocker, between the carrier and the rocker, you will find a retainer that limits the lateral play of the rocker. Investigate this on your machine and be sure to locate the retainer. The end play or side play of the rocker is limited or reduced to a minimum by loosening the set screw indicated by the green pencil and then moving the rocker shaft, indicated by the yellow pencil, from right to left. Since we are looking at the rear of the carrier in this picture, the shaft will have to move from left to right. In this manner, the retainer located on the left side in this picture will push against the right side of the rocker, thus limiting the lateral motion of the rocker. At that point, we should fasten the set screw and then check the adjustment for minimum end play of the rocker. The rocker can be regarded as the universal type bar of the Selectric typewriter. Consider that the element sitting on top of the rocker needs only to be rotated and/or tilted in order to turn up with the correct character. We explained earlier that we need to firmly hold the element in position at the time of printing, and that all of the adjustments which deal with holding the element at the time of printing are the fine alignment adjustments. The sequence we have to follow to take care of the alignment adjustments is extremely simple. We start with the carrier and work our way up to the type element. Let us briefly trace the mechanism which will ultimately lock the element into position prior to and during the printing operation. On the left side of the cam indicated by the yellow pencil, you will find a cam follower. This cam follower is the detent cam follower. The blue pencil indicates the detent actuator, which is allowed to move by the cam follower. It is also restored by the cam follower. The portion of the actuator indicated by the blue pencil will move from left to right under the action of the rather strong tilt detent spring connected to the tilt detent, right next to the point indicated by the red pencil. Another way of saying this is that the detent actuator lever, indicated by the blue pencil, allows the tilt detent, indicated by the red pencil, to rotate counterclockwise in this picture, under the action of the spring, which is fastened to the tilt detent right next to the point indicated by the red pencil. By turning the screw which constitutes the pivot point for the tilt detent at the yellow pencil, and also the screw located right behind the yellow pencil, we are able to restrict the lateral movement of the tilt detent sufficiently so that when it is engaged with the V-shaped cutout, the tilt ring is prevented from tilting or rotating in a vertical plane. When tightening the screw indicated by the yellow pencil and also the screw immediately behind it, we must be careful not to create any binds for the detent. Check the lateral play of the tilt detent on your machine. Holding the tilt ring in its position during printing with the use of the tilt detent is not yet all there is to locking the element into position. The element is supported by the indicated part, called the upper ball socket. The upper ball socket still has the ability to rotate within any one of the tilt positions into which the tilt ring can be locked. Rather than lock the upper ball socket to prevent it from rotating, the Selectric typewriter locks the element directly by a detent called the rotate detent. When the tilt detent is allowed to operate, it also releases the rotate detent, allowing it to operate. The rotate detent will come up under the action of its own spring, indicated by the yellow pencil. This spring is called the rotate detent spring. The portion of the rotate detent indicated by the green pencil engages with the teeth of the type element or the skirt of the type element. The purpose is to lock the element in any one of the tilt planes during printing. The red pencil indicates the portion of the rotate detent, which is acted upon by the tilt detent, whenever the tilt detent disengages the rotate detent after printing has been carried out. In order to properly see the components and the position of the rotate detent underneath the tilt ring, let us now remove the tilt ring from the yoke, the two arms which support the ring. We remove the tilt ring by loosening the screws indicated by the green and yellow pencils and by removing the retainer and the link indicated by the blue pencil. In some older models, you might find that on the tilt ring, at the point indicated by the green and yellow pencils, you have a pin which can be extracted once you have removed the retainer. Be sure not to lose the pin. After you have removed all the indicated items, you should half-cycle a print operation for any character, and the tilt ring will readily come out of the yoke. As mentioned, the yoke is the part which has the two arms indicated by the green and yellow pencils. The yoke supports the tilt ring. Be sure to use the correct Bristol wrench for the set screws indicated by the green and yellow pencils. Once the tilt ring is out of the way, it becomes easy to see how the yoke holds the tilt ring in its position with the indicated pivot studs. The studs for the tilt ring are held in position only by the set screws which we just loosened. To reinstall the pivot studs for the tilt ring during reassembly, we must use finger pressure. Here the green pencil indicates the part called the dog bone. It is positioned inside the part indicated by the yellow pencil, called the lower ball socket. With the upper ball socket, the dog bone, and the lower ball socket, we have basically a universal joint which allows us to rotate the upper ball socket, or the type element, at the same time that we tilt the tilt ring into any position. We can use any of the 4 tilt positions we need in order to print the chosen character. The blue indicator in this photograph shows the portion of the tilt detent which controls the rotate detent. The rotate detent is mounted under the tilt ring, and it came out with the ring when we removed it. As you examine the dog bone, you will find a slot for the pin in the upper ball socket and another slot for the pin in the lower ball socket. The wear in this portion of the rotate mechanism shows first on the dog bone, rather than on the pins in the sockets. It is important to check the wear on the dog bone prior to engaging in tilt and rotate adjustments. We will have difficulty placing the element into its proper position prior to engaging the rotate detent if there is excessive wear on the dog bone. The play which this universal joint allows the type element should never exceed 1/2 of the distance between 2 teeth of the skirt of the type element. Any wear noticeably greater than this requires replacement of the dog bone. This is the underside of the tilt ring. The green pencil indicates the point at which the rotate shoe restricts the lateral play of the rotate detent. Between the indicated shoe and the lock nut at the front end of the tilt ring, we must obtain 0 side play when the rotate detent is engaged with the notches in the skirt of the element. To adjust the position of the rotate shoe, we loosen the screw indicated by the yellow pencil. This, however, is not always easy, because when the tilt ring is installed in the machine, this screw is not easy to reach. With an offset screwdriver, or a very small screwdriver that fits into the slot sideways rather than from below, it is possible to loosen the screw. Moving the shoe by only a small amount and tightening the lock nut enables us to eliminate the side play of the rotate detent. Be sure not to create any bind for the rotate detent. The adjustment can only be performed satisfactorily when the ring is reassembled in the typewriter, and it is possible to test the side play of the element. One of the reasons for this is that the rotate detent does not move quite all the way up to the underside of the tilt ring when the element is in place. You should not be the least bit surprised if you need to spend 10 to 15 minutes on this adjustment when you try it for the first time. Notice also the amount of lubrication found in these mechanisms. When you clean a machine, be sure to properly relubricate these areas. There is a tendency for the office machine repairman not to grease these spots because they are barely visible, easy to forget, and hard to reach. Failure to lubricate these points will invariably shorten the life of the machine. Here we can compare the old-style tilt ring with the new-style tilt ring. The rotate detent shoes are substantially different. Notice on the new one, on the right-hand side, that the shoe is actually held by 2 screws, one indicated by the green pencil and one indicated by the yellow pencil. These 2 screws make it much easier to adjust the shoe. When adjusting it, you loosen the screw indicated by the green pencil and only slightly loosen the screw indicated by the yellow pencil. This condition enables us to rotate the shoe around the yellow screw. It then becomes possible to change the position of the rotate detent shoe by very small increments and not lose that position when you retighten the screw indicated by the yellow pencil. With the old-style shoe on the left, it becomes necessary to slowly and gradually tighten the screw, reposition the shoe, then give the screw another bit of a turn, again reposition the shoe. until finally you have hopefully achieved a condition which does not allow any side play for the rotate detent. In reality, this adjustment for the vertical play of the shaft, which holds the lower ball socket, called the rotate shaft, is an adjustment which has to be dealt with during the adjustments of the rotate tape mechanism. However, because it has an effect on the positioning of the element prior to the engagement of the rotate detent with the teeth of the element, or the skirt of the element, IBM considers this adjustment to be part of the fine alignment adjustments. Regardless of when we work in this area, we should make sure that there is a tiny bit of vertical play for this rotate shaft, not any more than 1/10 of 1 millimeter. But above all, we must be sure that no bind is created by our adjustment. The rotate shaft extends all the way through the rocker, and its end play is determined by the positioning of the rotate pulley, as we will see during the exploratory disassembly a bit later. All we need to do to obtain 1/10 of 1 millimeter of end play is to loosen the set screw for the rotate pulley and adjust the position of the pulley up or down on the indicated shaft. During the reinstallation process, we approximate the correct positioning of the type element by pointing the indicated pin on the upper ball socket in the 7 o'clock direction, as shown here. Actually, this positioning of the pin, which locks the element onto the upper ball socket, is completely immaterial until we have performed the rotate tape adjustments. We will study the rotate tape adjustments in Learning Program number 10-4B. Having properly lubricated the tilt ring and the lower ball socket, we can reinstall the ring. The tilt ring is reinstalled by applying finger pressure to the pivot studs which hold it in place. When we install the tilt ring, we should center it between the two arms of the tilt yoke, as shown here. As a last step in our efforts to secure the element during printing, we must make sure that the upper ball socket has no vertical play. To eliminate any vertical play from the upper ball socket, we choose the correct size shim and position it between the tilt ring and the tilt ring spacer. Shim sizes are listed at the end of the adjustments in the adjustment manual. It is not necessary to remove the tilt ring spacer mounted on top of the shims. We can easily replace one shim at a time. But whenever we have to remove the tilt ring spacer, we must also disconnect the rotate detent spring. And when we work with the rotate detent spring, we must be very careful not to stretch the rotate spring any more than we absolutely have to. If you come across this upper ball socket play at a time when you do not have the right shim, and you know the typewriter is used heavily so you cannot afford any downtime, it is acceptable to use a very fine sandpaper or an extremely fine stone to grind down some of the thickness of these shims, so as to eliminate all of the vertical play for the upper ball socket. Care must also be used in centering the tilt ring spacer. Should you ever come across a broken element that still has its center socket, or hub, intact, it is a good idea to grind off all of the characters until the only thing left is what you see on top of the tilt ring in this picture. A partially ground off element like this one lets us check the clearance that exists between the tilt ring spacer and the hub of the type element, as indicated by the yellow pencil. We must make very sure there is no physical contact of any kind between the hub of the element and the tilt ring spacer, and we need to check it all the way around the tilt ring. If your machine comes equipped with a new style tilt ring, you will find that there is a spring in it which tries to move the upper ball socket toward the front of the machine, toward the keyboard. This feature allows the rear portion of the tilt ring to make constant contact with the inside wall of the type element, so that when the machine prints, there is always solid contact between the tilt ring and the internal wall of the element. This is one more of the features aimed at improving the reliability, the durability, and the writing picture of the IBM Selectric Typewriter. The final adjustment in our sequence of fine alignment adjustments deals with the motion of the detents. When the detents are engaged, we must be sure they are fully seated between the teeth of the tilt ring and the type element. When they are disengaged, we also want to be sure they clear the teeth by a given distance. The source of motion for the engagement and disengagement of the detents is the detent cam. We have seen that the cam follower transmits the motion to the detent actuator, the actuator transmits it to the tilt detent, and the tilt detent transmits the motion to the rotate detent. Our first concern is the position of the cam follower with respect to the cam, which is described by a measurement requiring the hooverometer. With the hooverometer resting on top of the detent cam, the horizontal portion of the cam follower should lie underneath the number 1 scribe line on the hooverometer. This applies to machines with a late-level tilt detent mechanism. Older machines may come equipped with a roller between the cam follower and the detent actuator. On these, the horizontal portion of the cam follower should be placed above the number 1 scribe line, still with the hooverometer resting on top of the detent cam. This is a bottom view of the carrier. In order to adjust the vertical position of the detent cam follower, we have to loosen the indicated nuts, and there are 2 of them. When we make this vertical cam follower position adjustment, we must also consider that the cam follower should track on as much of the working surface of the cam as possible, in such a way that it barely fails to make physical contact with the print sleeve. Do not let the cam follower rub on the sleeve. Once this adjustment is set, it isn't likely to need refining. Notice the ribbon lift cam on the print sleeve, right above the indicated nut. It is important for the upcoming adjustments that the print sleeve have minimum end play. Loosen the ribbon lift cam, then hold the print sleeve to the right while holding the ribbon lift cam to the left, before retightening the set screw for the ribbon lift cam. Make sure not to leave any binds in the print sleeve rotation. When the machine is at rest and you manually tilt the element into its horizontal position, as shown here, from the side you can observe the clearance, or the distance, which exists between the skirt of the element and the rotate detent. That distance should be equal to 0.89 millimeters, roughly the equivalent of the thickness of the flat portion of the IBM spring hook. As we lead you through the following steps, feel free to pause anytime you need. Whenever your typewriter does not meet the described specifications, you should make the necessary corrections before continuing. The second characteristic of a correctly adjusted detent motion is that the clearance between the detent cam follower and the detent actuator arm should not exceed 0.25 millimeters when the cam follower is in the dwell of the detent cam. Here is the sequence for the detent motion adjustments. First, we position the detent cam on the print sleeve sideways, so that the skirt clearance equals 0.89 of a millimeter. Then we adjust the height of the detent actuator lever, so that when the detent cam follower is in the dwell of the detent cam, we obtain the 0.25 millimeter clearance at the indicated point. Occasionally, we might have to readjust the skirt clearance after making the adjustment to the height of the actuator lever. Now let us adjust the skirt clearance. You know that the detent cam follower exerts left-to-right pressure on the detent cam. In order to change the position of the cam, it is best to first loosen one of the set screws of the detent cam completely, so that the cam is held in position by only one set screw. After we have completely loosened one of the set screws, we cycle the machine until we can comfortably reach the second set screw with a spline wrench. Then we wedge a wide screwdriver between the print cam and the detent cam without exerting any force on it. The screwdriver, used as a wedge, enables us to loosen the second set screw without completely losing the position of the detent cam, since it is holding all of the detent spring tension. Now, depending on whether we had an excessive clearance or a lack of clearance, we move the cam to the left or to the right accordingly. The screwdriver also lets us change the position of the cam in very small increments. On recent level machines, and assuming that the detent actuating lever is in its original shape, the vertical position of the actuating lever has very little, if any, effect on the vertical position of the tilt detent, and therefore on the rest position of the rotate detent. The reason is that the edge of the tilt detent, which contacts the detent actuator lever, is almost perfectly vertical when the machine is at rest, and the detents are kept disengaged. The situation is totally different if we observe the resulting changes when the cam follower is in the dwell of the detent cam. We must first change the position of the actuator lever, and then rotate the printing mechanism until the cam follower is in the dwell of the detent cam. We are then able to observe the results. It is most important that we allow for some clearance between the cam follower and the actuator when the detent cam follower is in the dwell of the detent cam. If the clearance is not there, it indicates that the tilt detent is not fully engaged with the tilt ring. On the type sample, this problem would show up as poor vertical alignment. We repeat, the clearance between the actuator and the cam follower should be up to 0.25 millimeters. After we loosen the indicated nut, raising the position of the detent actuating lever brings us closer to the pivot point of the tilt detent, and as a result, we get more output motion for the tilt and rotate detents. When we lower the screw which holds the detent actuating lever, we move the actuating lever away from the pivot point of the tilt detent, and the total motion transmitted to the tilt and rotate detents is decreased. Old-style support screws for the detent actuating lever came equipped with an eccentric stud for mounting the lever. The objectives of the adjustments remain the same. A maximum of 0.25 mm clearance between the cam follower and the detent actuator when at the low point of the detent cam, and 0.89 mm skirt clearance when on the high part of the detent cam. With this, we conclude the adjustments called alignment or fine alignment adjustments. Be sure that you practice and know how to make the adjustments covered thus far. From now on, we can devote our time to the tilt and rotate tape mechanisms. First, we will cover their theory of operation, and then the sequence of adjustments. IBM covers the whole subject under the label character selection. Let us begin with the tilt mechanism. The purpose of the tilt mechanism is to rotate the element in a vertical plane, meaning that the top of the element rotates toward the front during the selection movement and toward the rear during the restoring movement. The purpose of the rotate mechanism is to turn the element within any one of the tilt planes, or positions, selected by the tilt mechanism. This means that the front of the element turns toward the right or toward the left. We studied earlier that all motions of any parts caused directly by the action of the motor are called positive motions or positive actions, and that all motions caused by the action of springs are called negative actions. It is very important that during the upcoming discussions we keep these facts in mind. Even to a relatively unskilled observer, it is quite apparent that we must be able to tilt and rotate the type element in precise increments of rotation. When we want to tilt the element so as to print the characters that are in the second band, or belt, on the element from the top, we say that we need one tilt increment. We can say the same thing in other words by stating that at rest, if all we did was cause the element to fly against the platen and print whatever happens to be facing the platen. On an adjusted machine, we would always obtain a Z. The Z is the home position character of the element. If, however, we wanted to print a T, indicated by the green pencil, we would need to tilt the element by one tilt increment. We would have to rotate the element in the vertical plane by an angle that allows us to print a T, the character in the second band, instead of a Z, the character in the first band. The character situated below T is the degree mark. In order to print it, we would need a rotation in the vertical plane of 2 tilt increments. Below the degree mark there is a J. In order to print the J, we would need a rotation in the vertical plane of 3 tilt increments. Therefore, we say that J is a tilt 3 character, T is a tilt 1 character, the degree mark is a tilt 2 character, and Z is a tilt 0 character. The motion for all of the tilt action is furnished by a mechanism called the tilt differential. These various amounts of motion are transmitted to the element by the tilt tape system, which we will study in just a minute. Let us repeat that the tilt motion which causes the element to rotate from Z, a tilt 0 character, to J, a tilt 3 character, is powered by the motor, so we say the action is positive. The restoring of the element from the tilt 3 position, the position in which it printed J, back to tilt 0, at which the element would print Z, is accomplished negatively, through the action of the tilt spring. Let us now assume that we wanted to print the at symbol, indicated by the yellow pencil, instead of the Z indicated by the green pencil. This requires rotation of the element in a counterclockwise direction, by an angle that enables us to shift from Z to the character right next to it, the at symbol in this case. The angle of rotation needed in this instance is called 1 rotate increment. Counterclockwise rotation of the element, when the element is observed from above the machine, is accomplished by the action of the motor. Thus, we call it positive rotation of the element. Be sure to commit these definitions to memory, because we shall use them very often in this program. If we now wanted to print a $sign instead of the Z, we would need rotation of the element in a clockwise direction. Rotation of the type element in a clockwise direction is accomplished by the action of a spring, called the rotate spring. Therefore, this rotation is negative. This is a view of the underside of the carrier, with the rotate spring exposed and clearly visible. The rotate spring supplies the force needed to carry out all of the negative rotation of the element. Negative rotation of the element is clockwise rotation for an observer placed above the typewriter. From this discussion, we can see that the Selectric uses both positive rotation and negative rotation for the element, so we also have positive rotate increments and negative rotate increments. With the sole exception of the shift mechanism, which is just a portion of the rotate tape mechanism and is not shown in this frame, all of the character selection is performed by the two indicated mechanisms, called differentials. The red pencil indicates the connection between the tilt tape mechanism and the tilt differential. The vertical link of the tilt differential, below the red pencil, is attached to the tilt bell crank. When the link is pulled down, it has the ability to turn the tilt bell crank counterclockwise, transmitting the motion from the tilt differential to the tilt tape mechanism. Notice that the tilt differential has two selector latches. The yellow pencil indicates the connection point between the rotate differential and the rotate tape mechanism. Specifically, the indicated stud establishes the connection between the large rotate bell crank, which is part of the rotate tape mechanism, and the balance lever, which is part of the rotate differential. On the left side, the balance lever is connected to the portion of the rotate differential, which generates positive rotation for the type element. On the right end of the balance lever, which is not visible because it fits inside the rotate bell crank, we find the connection to the flat link of the -5 rotate bale, which, as the name implies, delivers 5 negative rotate increments to the type element. Notice that the rotate differential has 4 selector latches. Be sure not to miss the -5 selector latch when you count the latches. Manually try to depress the tilt crank at the point indicated by the red pencil, and notice how the motion is transferred horizontally toward the left in order to rotate the tilt arm. You will notice that the tilt arm has a tilt pulley on top of the arm, and that around the pulley runs the tilt tape. The tilt tape has the ability to move the type element in a vertical plane. So that we can see the whole mechanism in one picture, let us turn to a drawing. This is a picture of the complete tilt tape system. We have seen that with a downward motion of the tilt latches, the tilt arm on the left-hand side is rotated counterclockwise, meaning that the left-hand tilt pulley moves toward the left. When we examine the way the tilt tape is mounted in the machine, we find that it is permanently anchored on the right side of the carrier. The pin shown here in red is actually mounted on the carrier frame. From that stud, the tape first goes toward the right side, around the right-hand tilt pulley, the position of which is adjustable, then all the way to the left side, around the left-hand tilt pulley, and back toward the carrier where it is fastened to the tilt pulley. The tilt pulley is really only a sector of a pulley, a portion of a pulley. Attached to the tilt pulley you find the tilt pulley link, which connects the tilt pulley to the tilt ring. Again, as we have seen earlier, the tilt ring holds the upper ball socket, and the upper ball socket holds the type element. Be sure to allow yourself enough time to familiarize yourself with all of these names. Then, as a second step, find these same parts in your machine so that you know how to trace the tilt tape system in your typewriter. Once you are fairly familiar with the part names, and once you have traced all of these parts in your machine, let us prepare for the dynamics of this mechanism. First of all, find the location of the indicated tilt pulley spring, and be sure to locate the spring in your machine. The tilt pulley spring is constantly pulling on the tilt tape to keep it taut around the tilt pulleys. If we consider that the tilt arm is movable, we can cause the tilt arm to rotate clockwise. It then becomes obvious that the tilt pulley spring is responsible for trying to move the tilt arm toward the right, into the machine. However, the left-hand tilt arm can only rotate by a limited amount. Through the brown link connecting the tilt arm to the tilt bell crank, the force of the tilt pulley spring is transmitted to the tilt bell crank. The bell crank is then trying to rotate clockwise at all times, also under the action of the tilt pulley spring. Why can it not continue to rotate? Because in order to rotate clockwise, the tilt bell crank must be able to lift the vertical link, which connects the bell crank to the green horizontal lever indicated by the blue wedge. That lever is caught between two red pads, which prevent the tilt latches from moving upwards. These pads, quite understandably, are called stop pads. In conclusion, we we may state that the tilt pulley spring is trying to make the tilt latches come up at all times. The tilt pulley spring transmits its force through the tape to the left-hand pulley through a horizontal link to the tilt bell crank, and through another vertical link to the tilt differential. The indicated lever and the latches are held up against the latch stop pads. Let us focus our attention on the lever indicated by the blue wedge. If we measured the point at which the vertical link coming from the tilt bell crank is connected to that lever, we would find that this point is located at precisely 1/3 of the lever's length away from the tilt 2 latch, and 2/3 of its length away from the tilt 1 latch. From our training in fundamental mechanics, we know that if we were to pull down on the tilt 1 latch, the total amount of motion experienced by the tilt 1 latch would be reduced by 2/3 by the time it is transmitted through the link to the tilt bell crank. This happens because the vertical link connecting the lever to the tilt bell crank is so much closer to the pivot point of the green lever. The stop pad above the tilt 2 latch provides the pivot point of the green lever. As a matter of fact, if the vertical link were positioned at exactly the same point where the tilt 2 latch is connected to the lever, we would find that the amount of output motion from the vertical movement of the tilt 1 latch would be equal to 0. Conversely, if the vertical link were connected directly above the tilt 1 latch, all of the input motion of the tilt 1 latch, or the latch bail for that matter, would be transferred to the tilt tape system. At this point, you should depress the character T and then hand cycle the machine while observing the indicated tilt 1 latch. Try to observe the amounts of motion that occur here. You should, for instance, notice that the vertical input motion of the selector latch, provided by the action of the cam follower or the latch bail, is a whole lot greater than the output motion of the link, which connects the latch lever to the tilt bell crank. It turns out that the tilt bell crank experiences only 1/3 of the motion obtained by the tilt 1 latch. Now cycle the same character T one more time and observe that the tilt 2 latch, indicated by the red pencil, remains in its rest position against the stop pad. It becomes obvious that the lever which connects the 2 latches uses the point indicated by the red pencil as the pivot point for this operation. We again summarize our observations by stating that using the tilt 1 latch only, the one on the right side, reduces the total amount of input motion to 1/3, so that only 1/3 of the vertical motion obtained from the positive latch bail through the tilt 1 latch is transferred into the tilt tape system. Now cycle the T again and observe on your machine that the tilt bell crank rotates counterclockwise and pushes the tilt arm away from the power frame of the machine, with the end result that the tilt pulley is moved toward the left, away from the carrier. Moving the left-hand tilt pulley away from the power frame is really pulling on the tilt tape, and somebody has to give. We know that the right end of the tilt tape is permanently anchored to the carrier frame, but the left end of the tilt tape is connected to the tilt pulley sector on the rocker, and it will rotate when we pull on the tilt tape. Observe also that once the tilt pulley sector is rotated, the link which connects the sector to the tilt ring causes the tilt ring to rotate by 1 tilt increment. 1 tilt increment being the angle of rotation needed to position the T character from the second band of characters on the type element in line for printing. At this point, you should hand cycle the degree mark or an exclamation mark and observe that because we pulled down the indicated tilt 2 latch, we obtain 2 tilt increments of rotation for the type element. See if you can provide the explanation which justifies this result. Pause here if necessary. Your explanation should have sounded somewhat like this. Considering that the link which connects the horizontal tilt differential lever to the tilt bell crank is positioned at a distance of 2/3 of the lever length away from the pivot point of the lever, the amount of motion obtained from the tilt 2 latch, when it is pulled down by the cam follower, is reduced to 2/3 of the total value by the time it is transferred to the tilt bell crank. 2/3 of the motion obtained from the cam and transferred to the tilt pulley sector at the carrier will cause the type element to rotate from its rest position to the 3rd band of characters, counting the bands from top to bottom. As a final step in this fact-finding activity on your machine, you should hand cycle a J, and observe that for a J, both selector latches will remain under the positive latch bail. Now the amount of motion transferred through the link to the bell crank is going to be exactly equal to the amount of motion obtained from the cam follower, since both latches are pulled down. This results in 3 tilt increments of rotation for the type element. We are thus in a position to print the character located in the 4th character band of the type element. An earlier style of tilt mechanism uses a different kind of tilt pulley and a different kind of connection between the tilt pulley and the tilt ring. As you can see in this drawing, it uses tilt gear sectors. As for the remainder, it is still the same. The tilt pulley spring, or simply the tilt spring, keeps the tilt tape taut. When the tilt pulley sector rotates, that motion is transmitted through the tilt gear sectors to the tilt ring, accomplishing the same thing we accomplished earlier through the tilt link. Here is the catch. To rotate clockwise, the bell crank would have to lift the vertical link up into the tilt differential, and that lever is caught against the stop pads, which keep the tilt latches from moving upward. So the whole system is held up against those latch stop pads, and the bell crank goes nowhere until a latch is pulled down. If your reasoning went to the lever ratio, well done. The link to the tilt bell crank sits 2/3 of the lever's length from the pivot at the tilt 2 latch's stop pad, so the tilt 2 latch delivers 2/3 of the cam follower's motion, enough to swing the element from rest to the 3rd band of characters. Now we turn our attention to the rotate tape system. This time, let us start with the rotate differential and use an exploratory approach from the detail to the general. At the end, you should be prepared to review the whole system. The objective of the rotate differential is the same as with the tilt differential, splitting up the motion obtained from the cam follower with the positive latch bail. This time, we split the motion into 5 different rotate increments. The selector latches, which are part of the rotate differential, are shown here with a black coating. Our pencil is pointing out the R1 latch or rotate 1 latch. To the right of it, connected to the same horizontal lever, we find the R2 latch. To the left of the R1 latch, we find the R2A latch. These 3 rotate latches are called positive rotate latches. To the right of these latches, you find a link going to another selector latch, which in this picture appears very shiny because of light reflection. This one is called the -5 rotate latch. Take some time to locate these latches in your machine. Pay particular attention to the location of the -5 latch. The objective of the rotate differential is to divide the motion obtained from the cam follower into 5 rotate increments in either direction. Whatever the number of increments obtained from the rotate differential, the motion is transferred through the big rotate bell crank, which you see above and to the right of the rotate differential. As seen so many times before, here again positive rotation is caused by the motor action, and negative rotation is caused by spring action. Before we move on with our description of the mechanism, notice that the rotate differential has 3 horizontal levers. The lowest one is indicated by the red pencil. It is unbalanced because it is divided into 3 sections, just as in the case of the tilt differential. Immediately above this horizontal lever, we have another differential lever, which is divided into fifths. The link which transmits the motion upwards is located at 2/5 of the length of the lever from the right extreme of the lever and at 3/5 of its length from the left extreme. The lever which is connected directly to the bell crank is called the balance lever. The balance lever is the only one of the levers with 2 equal arms, meaning that the rotate bell crank is fastened to its exact center, red pencil. On the left side of the balance lever, yellow pencil, a link connects it to the positive rotate differential. On the right side of the balance lever, green pencil, and inside the rotate bell crank, we have a link connecting the balance lever to the -5 rotate bail. Take some time now to retrace these explanations until you are capable of reproducing them on your own. It matters a great deal that you learn and use the proper names of the parts. Don't hesitate to go back and review until you are in full command of the subject. The motion of the rotate bell crank is transmitted to the rotate link at the point indicated by the blue pencil, and from the rotate link to the lever called the rotate arm at the point indicated by the yellow pencil. Finally, through the pulley on the rotate arm, red pencil, and the rotate tape wound around the pulley, this motion is transferred to the rotate pulley located underneath the rocker, or the type element. The best angle for observing the R-5 rotate, or selector, latch is this one, from the rear of the machine. The blue pencil points at the pivot point of the -5 selector latch. This pivot point is fastened to the power frame of the machine. The green pencil points at the adjustment screw, which is fastened onto the -5 rotate bail. The yellow pencil points at the spring, which restores the latch after each selection. Notice also the restoring springs for the positive selector latches. From above the machine, we can observe the -5 rotate cam and the R5 rotate cam follower, also called the -5 rotate bail. It is important to notice that at rest, the cam indicated by the yellow pencil is positioned so that it pushes down on the cam follower indicated by the green pencil. This tells us that at rest the cam follower has used all the motion it can get from the cam indicated by the yellow pencil, and that if it is to operate during a cycle that requires this mechanism, a spring must exist somewhere capable of causing the R5 bail to follow the cam. When we studied the input section, or the keyboard, we learned that the -5 selector latch releases the spring tension of a negatively powered mechanism. Using the pulleys, the rotate tape, the levers, and the links we have just studied, the spring which causes the R5 cam follower to follow the cam is the rotate spring, located at the bottom of the rocker behind this black plate. By removing the screw indicated by the yellow pencil, loosening the screw indicated by the green pencil, and also loosening the screw below the green pencil, we can uncover the rotate spring, which we will do for you now. You should not attempt to open the cage without first releasing all the spring tension, so let us first show you the points that are important for you to know. Later, we will ask you to disassemble these parts. While we hold the rotate spring in position to keep it from flying out of its cage, you can now see the rotate spring and the indicated point at which it is fastened to the rotate pulley. The pulley, in turn, is fastened to the rotate shaft with a set screw. Notice that when viewed from below, the spring is constantly trying to rotate the rotate pulley, or shaft, counterclockwise, keeping the rotate tape taut. Don't let this confuse you. When viewed from above the typewriter, this becomes clockwise rotation. The rotation of the rotate spring means that the rotate spring tries to rotate the element in a clockwise direction when observed from above the typewriter. The other end, the outside end of the spring, is fastened to the spring cage. We remember from fundamental mechanics that a spring must always be held at 2 points at least. The green pencil indicates a small anchor spring. It is the point at which the spring cage, and thus the outside of the rotate spring, is locked onto the frame of the rocker. Since the rotate tape is connected to the rotate pulley, which is free to rotate, we conclude that the rotate tape is kept taut by the force that comes from the rotate spring acting on the pulley at the point indicated by the yellow pencil. When we reassemble the plate that sits underneath the rocker and holds the rotate spring in its cage, it is absolutely necessary that we mount the plate perfectly centered around the rotate pulley hub, as indicated. The slightest bind would interfere with the movement of the element and retard its operation during printing cycles. At this point, see if you can trace the force stored in this rotate spring from the rotate pulley hub all the way to the R5 bail, or cam follower. Don't forget to include the so-called shift mechanism, which is very much a part of the rotate tape system. This shows the entire rotate system in one view. Use your typewriter as often as possible for tracing the negative power or motion in your rotate mechanism, and take a moment now to work through this assignment. Your answer should have sounded something like this. The rotate spring tries to rotate the rotate pulley clockwise, pulling on the rotate tape. One end of the rotate tape is fastened to the rotate pulley, the other end is fastened to the carrier. On the right side, because the rotate spring is constantly pulling on the tape, the tendency is to rotate the shift arm counterclockwise, either against the high lobe of the shift cam or against the stop screw in the power frame. On the left side, for the same reason, the spring tension, the tendency of the rotate arm is to turn clockwise, causing the rotate pulley to move into the machine, toward the power frame on the left side. As a result, the rotate link at the bottom of the rotate arm is pulled toward the left. The motion is transferred to the rotate bell crank, shown in red in this picture, and the rotate bell crank is constantly trying to lift the balance lever. On the left side of the balance lever, the upward motion is stopped by the stop pads, which are colored red here. On the right side, the balance lever is connected through a link to the R5 cam follower. When the machine, or the cycle shaft, is at rest, the R5 cam follower is pushed down by the cam until the -5 latch locks the bail, or cam follower. But it is the rotate spring that ultimately keeps the -5 bail pulled up against the cam. Be sure that you fully understand this explanation before continuing, and take extra time if you need it. We are about to engage in a rather thorough explanation of the rotate differential, so you may want to return to this point later if you wish to hear the explanation again. The balance lever is divided into two equal parts. It is connected to the rotate bell crank at its exact center. Going down on the left side, the balance lever is connected to another lever, colored blue in this picture, which you should think of as being divided into 5 equal parts. On the right of this blue lever, it is connected to a third lever, which is divided into 3 equal parts. On the blue lever, the link connecting it to the balance lever is fastened 3/5 of the length of the blue lever away from its left end, where the archway selector latch is connected. That leaves 2/5 for the other end, on the right-hand side of the blue lever. The green lever, which holds the R1 and R2 selector latches, has a link connected between it and the blue lever, fastened 2/3 of the lever's length away from the R1 latch and 1/3 away from the R2 latch. We remember that the rotate spring is constantly trying to rotate the bell crank clockwise. For the crank to rotate, either the left or the right end of the balance lever must allow it to. On the left side of the balance lever, between the selector latches and the balance lever, are the stop pads, colored in red. Notice the -5 selector latch, visible in yellow at the bottom of this drawing. On the right side, the balance lever is connected through a link, called the flat link, to the -5 bail, and the -5 bail is latched down by the -5 or -5 selector latch unless we release it. Through the combined action of the stop pads, preventing the positive selector latches from moving upward, and the -5 selector latch, preventing the -5 bail from moving upward, the rotate bell crank is prevented from rotating clockwise. It is important to know that the total vertical motion obtainable from the -5 bail is exactly the same as the total vertical motion obtainable from the positive latch bail. If we were to allow the -5 bail to rotate upward, and at the same time pull down all of the positive selector latches with the positive rotate bail, the balance lever would move up on the right end and down on the left end by an amount equal to 5 rotate increments. But the end result would be that the center of the rotate bell crank would not change position at all, because both arms of the balance lever are exactly the same length. Since the link connecting the balance lever to the blue lever is attached 3/5 of the lever's length away from the archway selector latch and 2/5 away from the link on its right end. If we pull down only the archway latch with the positive latch bail, by the time this motion reaches the balance lever, it is only 2/5 of the motion experienced by the archway selector latch. When we pull the archway latch alone, the link connected to the right end of the blue lever provides the pivot point for the blue lever. Now let us filter out the archway selector latch and leave the R1 and R2 selector latches under the positive bail. Because of the position of the link between the balance arm and the blue lever, this time the total motion transferred from the R1 and R2 selector latches to the balance lever is 3/5 of the motion experienced by the selector latches. To make it simple, think of this link connecting the blue and green levers as being capable of transmitting a maximum of 3/5 of the total motion attainable from the positive latch bail. Reviewing it, then, the motion of the positive rotate bail is cut down to 2/5 of its original magnitude when only the archway selector latch is pulled down, and it is cut down to 3/5 when only the R1 and R2 selector latches are used. These 3/5 can be cut down further by the green lever, which connects the R1 and R2 selector latches. Now let us hypothetically filter out the archway and R2 selector latches and pull down only the R1 selector latch. Because the link connecting the blue lever to the green lever is located 1/3 of the lever's length away from the R2 latch, above which the stop pad functions as the pivot point for this operation, the total motion transferred to the blue lever is only 1/3 of the vertical input motion. That means that the balance lever, we obtain only 1/3 of the 3/5 maximum motion possible at the right end of the blue lever. And 1/3 of 3/5 is 1/5. By the same reasoning, using only the R2 selector latch while filtering out the R1 and archway latches yields 2/3 of the 3/5 maximum motion attainable at the end of the blue lever. And 2/3 of 3/5 is 2/5 of the total motion. Let us summarize all this. To obtain one rotate increment, the input section, or keyboard, leaves the R1 latch under the positive rotate bail while filtering out the other latches. To obtain +2 rotate increments for the element, the input section leaves the R2 selector latch under the bail while filtering out the R2A and R1 selector latches. For +3 rotate cycles, the machine pulls down the R1 and R2 selector latches. For +4 rotate cycles, the machine pulls down the R2 and R2A selector latches. For +5 rotate cycles, all selector latches are left under the bail. The R2A latch is never used alone on Selectric typewriters used as standalone office typewriters. We know that the positive selector latches cause counterclockwise rotation of the element. The R1 latch delivers 1/5 of the total motion of the positive latch bail. The R2 latch delivers 2/5 of the input motion received from the positive latch bail. And the R2A does the same thing as the R2 latch. It delivers 2/5 of the total motion received from the bail. All of this motion is transformed by the rotate tape system into rotate increments for the type element. Recall that releasing the -5 bail produces 5 increments of type element rotation in the negative direction, clockwise rotation, as the machine is viewed from above. When we need less than 5 increments of rotation in the negative direction, we simply use the needed amount of positive rotation together with a -5 rotation. Thus, a -4 rotation character is obtained by selecting the -5 latch to release the -5 bail, and filtering out the R2 and archway latches so as to also obtain +1 rotation. -5 rotate increments together with +5 rotate increments yields 0 rotate increments. Another example, if we wanted a -2 rotation factor for the type element, we would pull the R5 selector latch to release the -5 rotate bail and filter out the R2A selector latch, leaving the R1 and R2 selector latches under the positive rotate bail. The result, -5 + 3 yields -2 rotate increments for the type element. In your adjustment manual, you will find this chart, which shows how the 88 characters are laid out around the outer surface of the standard United States type elements. The distinction between uppercase and lowercase characters is made by moving the right rotate pulley, using the mechanism called the shift mechanism, although it doesn't actually shift anything. Whenever the shift mechanism operates, it merely rotates the element by 180 degrees or 11 rotate increments. Rotation is positive when the machine is set up to select capital letters, and negative when it is set up to select small or lowercase letters. Within each block or rectangle, the selection between the horizontal lines is accomplished through the tilt mechanism. The tilt latches, which must be pulled down by the positive latch bail, are indicated at the right end of each line. The rotate latches to be pulled down are indicated at the bottom of the chart. The latches that are not mentioned must be filtered out by the input section, or keyboard. This process is called negative true logic. Some people call it reverse logic. The keyboard picks the latches which should not be used. The input section literally filters out the unwanted latches using the filter shaft, leaving under the positive rotate bail only those latches which are to be pulled down. It is quite another story when it comes to the -5 rotation and the printing velocity selection. If those latches are selected, they release the corresponding mechanism, so in that case the machine uses positive true logic. Be sure to review this operational theory as often as you need to, replaying this explanation and tracing out the mechanism on your machine. You should randomly pick some characters, hand cycle them, and observe which selector latches are pulled down or filtered out. That way you can convince yourself that this chart is accurate. After this, we will devote our efforts to the disassembly, reassembly, and adjustment procedures of the output section of the IBM Selectric Typewriter. If you traced its spring to pulley to tape, you have it. The rotate spring pulls the tape taut, tending to turn the shift arm against its cam or stop screw on the right and the rotate arm clockwise on the left, which pulls the rotate link into the bell crank. The bell crank tries to lift the balance lever, stopped by the stop pads on the left, and on the right it holds the -5 bail pulled up against its cam, where the -5 latch locks it at rest. There are various ways to take out the tilt and rotate tapes. We will show you one that starts with the right end of the tapes. As you examine the anchor spot on the right frame of the carrier for the tapes, you will find that the rotate tape is located at the bottom. Therefore, in order to take out the tilt tape, we must always first remove the rotate tape from this anchor spot. The job is actually very simple, because all we have to do when we want to work with the tapes is first remove, or somehow relieve, the spring tension so we can handle the tapes freely. Let us start by removing the spring tension from the rotate tape. We know that the rotate spring tension acts on the type element, trying to turn it in a clockwise direction. If we manually turn the type element counterclockwise, we are automatically unwinding the rotate tape from the rotate pulley underneath the rocker. So let us rotate the type element manually, counterclockwise, 1/4 of a turn, and then half cycle at T until the rotate detent engages with the skirt of the element to hold it in place. We can now let go of the element because the rotate detent holds it for us. At this point, follow along by doing the same thing on your machine. By disconnecting the tilt spring from the tilt pulley indicated here, we also remove that spring tension. Take a moment to perform this step as well. Since we have removed the spring tension from the tapes, we are now in a position to remove the anchor screw from the tapes. Let us do that now. Once we have disconnected the tilt tape, we can temporarily reinstall the rotate tape. A pair of tweezers is a handy tool for this job. The rotate tape has been reconnected to the anchor. We make sure it has been properly threaded or laid out around the pulleys, and then we can release the spring tension again. The purpose of releasing the rotate spring tension at this point is to make sure the rotate tape is kept taut while we work with the tilt tape. As you perform this step, make very sure that you release the rotate spring tension slowly, so that if the tape were to come off any of the pulleys without your noticing, you could still catch it and reposition it before you develop a kink in the tape. The other end of the tilt tape is connected to the tilt pulley sector mounted on the rocker. After you have thoroughly inspected the way the tilt tape is threaded, particularly under the escapement plate or bracket, go ahead and remove the tilt tape from the machine. It is important to avoid bending the tape too much, which can happen easily when trying to remove it from the tilt pulley sector. On older machines, instead of the nylon pulley indicated by the green pencil, we might find a metal pulley or even a horizontally mounted metal pulley sector on the geared tilt mechanism. Whatever the modification, the basic process of removing the tilt tape is the same as the one we have demonstrated. In order to grasp the right end of the tilt tape with tweezers, as shown here, you may need to feed some of the tilt tape into the carrier with your left hand to build up enough slack around the pulley. Once you have removed the tilt tape from your machine, it is time to reinstall it. Simply reverse the order of the steps you used to remove it. Start by installing the tape on the indicated stud on the tilt pulley or tilt pulley sector. Then feed the tilt tape around the left tilt pulley, underneath the escapement bracket, and out through the opening in the right side of the power frame. Once again, in order to remove the anchor screw, we must first remove the rotate spring tension from the rotate tape. We do this by rotating the element counterclockwise approximately 1/4 of a turn, then half cycling a character so the rotate detent can lock the element into position. Take the time you need to complete this. Now we can reinstall both tapes onto the anchor screw in their proper order. The tilt tape goes on top and the rotate tape goes on the bottom. It is very important to make sure there is no twist or kink in the tape from mishandling during removal or reassembly. A sharp bend will require tape replacement. Once both tapes have been fastened onto their anchor screw, we must again carefully release the rotate spring tension. If at this point you do not yet have the tilt tape around its pulleys, don't let it worry you, simply continue. In order to obtain maximum slack for the tilt tape, we tilt the type element all the way toward the front. It then becomes quite easy to install the tilt tape around the left and right tilt pulleys. Our last step in reinstalling the tilt tape is hooking up the tilt spring. Had this been a repair job, we would now be ready to adjust the tilt mechanism. However, before we start with adjustments, we will first practice removing and reinstalling the rotate tape. The rotate tape breaks far more often than the tilt tape, and it is very important that we become proficient at replacing rotate tapes. This time, when removing the rotate spring tension from the rotate tape, we will go a lot further. We start by closely watching the rotate pulley while we turn the element counterclockwise. We keep turning the element counterclockwise until we find the condition indicated here by the green pencil. Notice that the rotate tape is on its last turn around the pulley, and we must be very careful not to turn the element counterclockwise too far, or we will break off the tip of the rotate tape. Once we have arrived at the condition shown here, we again half-cycle a character so that the rotate detent can hold the element in this position. We use the left hand to push a little bit of rotate tape into the carrier cavity. The extra slack allows us to apply a spring hook behind or under the rotate tape at the point where it is connected to the rotate pulley, between the rotate tape and the carrier. The indicated shoe over the pulley on the rotate arm has the purpose of preventing the rotate tape from accidentally jumping off. This shoe does such a good job that in order to remove the rotate tape, we must loosen the screw and pull the shoe away from the pulley by approximately 3 millimeters. As you loosen it, notice the angle it occupies on the rotate arm. It should be at approximately 150 degrees when viewed from the front of the machine. Be sure to place it into the same position again during reassembly. As soon as you have removed the rotate tape shoe on top of the rotate arm, your tape is free, with the exception of the anchor screw on the right side of the carrier, and by now you know how to handle that. Prior to loosening the anchor screw, take off the tilt spring tension so that the tilt tape cannot snap. Now we could go right back to reinstalling the rotate tape, but rather than do that, let us first continue with our exploratory disassembly. Notice the indicated small arrow on top of the type element. It is now possible for us to release the rotate spring tension and tell exactly how many turns it takes for the element to come to rest. In other words, we can find out how many turns of spring tension are loaded into the rotate spring when the system is completely assembled. At this point, let us release the rotate spring tension. First, we hold the element with our left hand and continue to turn the hand cycle wheel so that the rotate detent comes out of engagement with the element. Then, we slowly allow the element to rotate clockwise and count the number of turns it takes until the element comes to rest. The spring took slightly more than 3½ turns before it exhausted its tension. This is correct. We should have approximately 3½ turns of tension on the rotate spring before we install the rotate tape. But let us not install the rotate tape yet. Let us first remove the tilt tape and then also the cords so that we can remove the carrier. We might as well extract the tape anchor spring at this point. Now let us remove the escapement bracket entirely from the carrier. Also remove the print shaft. If you have not yet extracted the tape anchoring screw, do it now. And while you are at it, remove the tilt tape from the tilt pulley sector once again so that we can lift the carrier out of the machine. Once all this has been done, we can remove the carrier from the machine. With a rag placed over the keyboard, we can easily set the carrier upside down on top of that rag and work on it without even having to remove the velocity control cable from the carrier. Try not to twist the velocity control cable unnecessarily. One of the reasons we wanted you to take the carrier out like this was to investigate the purpose and construction of this rotate tape guide. Remove it now by extracting the 2 screws which hold it in position. During any negative rotation of the type element, when the excess rotate tape is being taken up around the rotate pulley, the tape is guided onto the rotate pulley by this guide shoe. It is important to be aware of this when installing the rotate tape, so that we properly place the tape around the shoe and not above it or below it. Let us also remove the plate which covers the spring cage. It is now possible to remove the spring and its cage entirely from the rocker. Before you remove the spring, notice that the outside end of the rotate spring is located at approximately the 9 o'clock position in this picture. We should be aware of this fact and retain this position if we want to have the exact same 3.5 turns of spring tension at the end of the reassembly process. This, however, is not at all critical because we can adjust the spring tension once the whole mechanism is assembled. As you remove any parts, observe as much as you possibly can on them and make it a point to study the machine. For your convenience, we have temporarily reinstalled the rotate tape shoe so we can visualize its function in the machine. With the rotate spring cage removed from the rocker, the rotate pulley is conveniently exposed. The green pencil in this picture shows the direction from which the rotate tape comes into the rocker. The rotate tape guide simply ensures that the tape will properly track into the groove of the rotate pulley, indicated by the yellow pencil. To remove the rocker from the carrier, you would have to remove the rotate pulley, because the outside edge of the rotate pulley extends into the cutoff section of the pivot shaft for the rocker. This pivot shaft is located underneath the rotate pulley in this picture. By loosening the screw indicated by the green pencil, it is possible to remove the rotate pulley from the rotate shaft, indicated by the blue pencil. Again, be sure that you choose the correct tool for the set screw, which holds the rotate pulley in place. With the rotate pulley out of the rocker, we discover that the tilt tape pulley also extends into the pivot shaft of the rocker, which has been cut in half at the point indicated by the green pencil. Obviously then, in order to remove the rocker shaft, we must also remove the tilt pulley. Notice this wiper washer around the screw, which functions as the pivot point for the tilt pulley sector. This wiper washer should be kept impregnated with light typewriter oil so as to always keep the pivot point for the tilt pulley sector properly lubricated. Wear on this hub of the tilt pulley can affect the tilt detenting and, indirectly, the rotate detenting, causing poor alignment. The same criteria apply to the wiper washers around the print shaft. If we fail to keep them properly lubricated, we end up with worn bearings for the print sleeve. The effects of this wear vary from escapement malfunctions all the way up to poor alignment. While it is only a minor job to replace the tilt pulley sector or the print sleeve bearings, if and when you can get them, it becomes a major job if you have to replace the whole carrier frame. Once you have disassembled your carrier to this point, take time out to examine it very carefully to see just how many, or how few, parts are left on that rocker. Actually, it should become apparent now that the system is not very complex at all, and the concept of the universal type bar performing all the printing on the IBM Selectric Typewriter should now be clear to you. Let us now disassemble the parts which constitute the rotate detent. The first part is the rotate pulley. Once we have removed the spring which fits around the hub of the rotate pulley, we can pull out a wedge, which in this picture is positioned to the left of the pulley. The set screw on the rotate pulley always presses against the wedge instead of pressing against the shaft. This way, we can very accurately position the rotate pulley and prevent any kind of burr or mark on the rotate shaft from interfering with the adjustment of the position of the element. When we position the rotate pulley back onto the bottom of the rocker, we have two dimensions to consider. One is the angular position of the rotate pulley, which we will take care of later, and the second is the vertical position of the pulley on the rotate shaft. We should position the rotate pulley on the rotate shaft so that the shaft has approximately 1/10 of a millimeter of end play. This can easily be checked under the lower ball socket, as shown. Since later on, we have to adjust the angular position of the rotate pulley, for the time being we just approximate this clearance. When we adjust the angular position of the element with respect to the pulley, that is when we also adjust the vertical position of the rotate pulley, making sure that we meet the 1/10 of 1 millimeter clearance at the indicated spot. Now let us turn to the reinstallation of the spring cage, with the spring inside it, underneath and around the rotate pulley. First, notice that the spring is held on one end at the point indicated by the green pencil, directly to the spring cage. The point indicated by the blue pencil engages with the hub of the rotate pulley. Notice also the wings, just like petals, which extend out at the outer rim of the cage. These wings provide ideal holding spots for the spring cage when it is installed at the bottom of the rocker. When the rotate spring is under tension in a fully assembled machine, the center end of the spring is held by the rotate pulley, and the rotate pulley is held by the rotate tape. The outside end of the spring is held by the spring cage, and the outer rim of the cage is held by the retainer spring indicated by the green pencil. Let us point out once again that this retainer spring is fastened directly onto the rocker frame, and that it functions just like a ratchet pawl, so that through the spring it becomes possible to increase or decrease the rotate spring tension. Thus, we are able to turn the rotate spring cage while the rotate pulley is held stationary by the rotate tape. When reinstalling the cover plate for the rotate spring, make very sure that there is no point of contact anywhere between the hub of the rotate pulley and this plate. We must make sure that when the machine is completely assembled, there are no hidden binds or heavy spots for the rotate pulley to overcome. Remember that the rotate pulley determines the position of the type element. Before we reinstall the carrier, take a good look at the parts of the printing mechanism. Here, for instance, the yellow pencil shows the roller of the print cam follower, and the green pencil points at the anchor spot for the shield or tube of the velocity control cable. You should examine in detail how the print cam follower is pulled towards the left, into the path of the low velocity lobe, and how it is restored back towards the right after the printing of a low velocity character. All of this is much easier to see when the carrier is out of the machine. Take this instance, in which we are trying to show you the small spring which returns the print cam follower into the path of the high velocity lobe on an assembled machine. This is much easier to observe when the carrier is out of the machine, and you should make the most of it now, so that later you no longer need to disassemble the machine in order to work on the rocker. Notice also this small guide spring for the velocity control cable. It is extremely important to be aware of the function of this guide spring when working with the dual impression machines. This guide spring prevents the velocity control cable from becoming entangled with the carrier return pulleys when the carrier is at the extreme left margin. It simply keeps the cable above the cord pulleys. The velocity control cable should be clamped into place in such a way that it only lightly touches the inner surface of the power frame when the carrier is at the extreme left position. This, of course, can only be checked when the carrier is back in the machine. Notice this nylon shoe called the buffer. It touches the carrier support rail during printing. Depending upon the level of your machine, you might have a buffer of a completely different design. Earlier models had adjustable buffers. This one is not adjustable. In this case, we must adjust the position of the carrier support rail. Once you are satisfied that you have mastered all of the mechanisms of the carrier, reinstall the carrier, the escapement plate, the cords, and the tilt tape before moving on to the reinstallation of the rotate tape. We start the reinstallation of the rotate tape by hooking it up to the anchor screw at the right side of the carrier. Then route it around the shift pulley, or, in the case of some older style shift arms, through the shift arm under the carrier and out the left side of the power frame. When you reinstall the rotate tape, make sure that the bottom portion of the rotate tape loop, indicated here by the green pencil, is placed underneath the carrier return cord, indicated by the yellow pencil. You will not be able to adjust the rotate tape system if you fail to do this. Reinstalling this guide shoe at this point, if your machine has one, will help you keep the rotate tape around the pulley of the rotate arm. Make sure that no friction of any kind is developed by this shoe, neither on the tape nor on the pulley. Observe also the angle at which it is positioned, approximately 150 degrees when viewed from the front. Do not make this angle any smaller, because the shoe might otherwise interfere with the tape when the rotate arm sweeps clockwise, all the way into the -5 rotate position. The same is true for the +5 position of the rotate arm if the angle is much greater than 150 degrees. Our first step in the reinstallation of the rotate tape onto the rocker is reloading the rotate spring. We simply rotate the element counterclockwise 3½ turns from the position indicated here, and then lock the spring tension into position by half-cycling a character, so that the rotate detent can engage with the skirt of the type element. Before you half-cycle a character, however, make sure that you have the T-shaped slot in the rotate pulley facing the front of the machine, where you can readily see it and get at it. If you have to turn the element slightly more or less than 3.5 turns in order to get the rotate pulley to position the hookup point for the rotate tape towards the front of the machine, think nothing of it. We can always make it up by rotating the spring cage, as explained earlier. Once we have half-cycled a character and lock the element into position, we are ready to install the rotate tape. While we attempt to install the rotate tape, we must be very careful not to act on the detent cam follower or the detent actuator arm, because inadvertently releasing the rotate detent will allow the spring to discharge all of its tension very quickly, with a very good chance of breaking off a tooth of the element. Up until this point, the rotate tape was installed with absolutely no twist in it. When we go from the left rotate pulley, the pulley situated on top of the rotate arm, into the carrier, we have to introduce a half-turn twist for the first time. This is a picture of the rotate tape already installed. The objective here is to show you which way the rotate tape was twisted prior to being inserted into the opening of the rocker shaft. Notice that the tape was twisted on the right end, top towards the front, so that during printing, when the tape has to twist with the rocker movement towards the platen, the tendency is to untwist the tape as the element moves towards the platen. Of course, when the element comes back to rest, it twists the tape again, into the condition shown here. Once we have properly turned and twisted the tape, we must know that the rotate tape is inserted under the tilt tape, as shown here, for the obvious reason that the rotate pulley is mounted on the rocker underneath the tilt pulley. Feed the tape all the way through the rocker shaft and lay it above the escapement bracket, as shown here. Using 2 pairs of tweezers is by far the most practical method of feeding the tape through the rocker, over the rotate pulley, until it comes out at the front of the rocker. But if you do not have 2 tweezers, or do not like to use them, you can even do this with your bare hands, with the sole reservation that you should be very careful not to cause any sharp bends in the tape. Be sure to recheck the direction of the tape twist before you feed the tape through the rocker. This is a time when the IBM spring hook is an almost indispensable tool. With the flat end of the spring hook, you can grab and hold the T-shaped tip of the rotate tape as shown here. Holding the tape, this way lets you rotate the tip into the position needed to hook it up with the rotate tape pulley. All you need in addition is a small screwdriver to push the T-shaped tip into the slot. Be very careful not to release the rotate detent by inadvertently moving the detent cam follower or the detent actuating lever. Here you can see how to handle your tools while you hook up the tape. Now we need to position the rotate tape properly around the pulley, around the guide shoe we studied earlier, and around the pulleys on the shift arm and the rotate arm, so that we can release the engagement of the rotate detent. While you align the tape around the rotate pulley and the guide shoe on the rocker, use a small screwdriver held over the T-shaped end so it does not lose its position while you work the tape around the pulley. Once you have guided the tape properly around the rotate pulley, there is no need to hold it in place any longer. At this point, we are ready to release the rotate spring tension. First, hold the element in position while you complete the half cycle that was locking the element. Then slowly release the spring tension, watching very carefully the whole time that the tape does not come off any of its pulleys. If you haven't already done so, reconnect the tilt spring at this point. Because the rotate mechanism is so critical, we need to be able to test and measure the spring tension of the rotate spring. To set up the machine for this measurement, half-cycle a small letter M and then remove the type element from the typewriter. Then use a spring gauge and press it against the shift arm as shown, moving the shift arm out of the machine. You should measure 900 grams, or almost 1 Newton of force, when the shift arm leaves its rest position against the stop screw in the side frame. Grams isn't really a correct unit for force, but for the time being we have to live with it because many of our force measuring scales indicate grams. You may even come across an old scale that uses pounds as its unit of force. To use such a scale, you should know that 900 grams is approximately equivalent to 2 pounds. Whenever we view the rotate spring from above, we rotate the spring cage clockwise to increase the spring tension and counterclockwise to decrease it. Rotating the spring cage clockwise to increase the tension is a simple matter, since the spring indicated by the yellow pencil acts like a ratchet, locking it in place every so often so the spring cage cannot turn counterclockwise and discharge the spring tension. If, however, we want to decrease the spring tension, we must use another tool to control the spring cage and then go to the spring indicated by the yellow pencil. Hold it out of the way of the rotate spring cage while allowing controlled amounts of counterclockwise rotation of the spring cage. When you take the ratchet spring out of the way of the spring cage, be very careful not to force or bend the little spring. The rotate mechanism is very likely to sustain damage if you let the spring tension escape all at once. This concludes Package 10.4a. To learn how to perform the tilt and rotate adjustments, continue the program with Package 10.4b.